Welcome back, students, to differential equations, reg calculus. I hope you guys had a great New Year and a good Christmas, and hope you guys spent a lot of time enjoying your break. So now that we're back to class, I want to make two very important announcements. The first announcement is that the course syllabus for reg calculus and our course outline has been changed. So we have bumped the amount of lectures from a couple to 15 lectures. So this course will contain 15 lectures wherein you guys and newcomers will have to complete in order to pass the course. And so these includes actual topics from differential calculus. I'm gonna be using a reference material. We have a parent material for this course, and that is Elementary Differential Equations by Rainville and Bediant. That's our parent material, and if you wish to follow along with this course, I highly suggest you guys pick up a copy of that. Many bookstores are actually selling that, so you guys can check it out. So, in the previous lecture, we talked about flux in the flux W equation. And the flux W equation states that the double integral of flux is equivalent to the single integral of the variability. Hence flux in W. And my derivation in the previous lecture actually is very sloppy. It wasn't structured so well. So in this lecture, I'll give you guys a re-derivation of the equation. So we know from the notations episode that flux is equal to the second derivative of choice with respect to time, and that if we take the double integral of both sides, we get the double integral of flux with respect to time squared, dt squared, is equal to the choice, right? So that's fact. Next fact is that variability, we know that the variability is equal to the change in the appearance with respect to time. So if we take the integral of both sides, this d would cancel out, and we get the integral of w with respect to time is equivalent to the appearance. So that's A. And so, alright, so we all know the fundamental axiom of congruence, and that states that the appearance is equal to the choice, and so gender congruence actually. And so inputting the equations or the facts that I've said here, we get our flux W equation over here. dt squared is equal to integral of w dt. Quadrat demonstrandum, box, to end the proof. People like to write QED, but I'll write box to end the proof. And now this involves a lot of integrals actually. As we notice, if you guys will notice, if we take the derivative of both sides, the variability is actually equal to the integral of the variability, the integral of the flux with respect to time. So if we treat flux as a function of time, then, or well, make a graph of it, then some area between two bounds over here tells us the variability. And this demonstrates to us the importance of integrals. Now, our study involves a lot of derivatives and changing things, but I also want to emphasize the importance of integrals. This wouldn't be calculus without integrals, so of course we're going to add integrals into there. So if we have a graph of t, some area under the graph between two bounds is our variability. And that's a perfect segue to today's lecture, because today's lecture is about area, how area relates to our quantities and various relations that hold because of this relation or this topic. And so let's begin by, I actually want to adopt a notation which is used by most mathematicians. It's used by Lagrange, and that is the dot for derivative. So the dot notation for derivative is that c dot is basically C dc over dt, which is, well, C dot. And from here, I can say that the second derivative, or C double dot, is equal to the flux, because that's the second derivative of C with respect to time. Alright, and so from here, it is easily found that the double integral of flux is actually the confidence. So if we have a graph of ft, this area that I've stated about is the confidence. The choice. It tells us the choice between these two intervals. And actually, since it's a double integral, I'm inclined to write v here, and inclined to write dv here, because another way to interpret this double integral is as a surface of revolution. So let's say that this is the graph of f of t. Suppose we revolve it around the y-axis. It will turn into a three-dimensional object. Known as a surface of revolution. And we have a surface of revolution. The relation of a double integral with a surface revolution is that this double integral tells us the volume of the surface of revolution. It tells us the volume. So the volume of the surface of revolution, which is described by rotating the graph of f around an axis, the volume of that surface of revolution tells us the choice. And so I want to include one more situation of area before I conclude the lecture. Is that wouldn't it make sense that the change in the appearance is also equivalent to the inclination? So the change in sort of the confidence of the change of the wear, or the change in the derivative of the wearability is equal to the change in the appearance with respect to time wearability. Would that make sense? That it's that would be the case. Our confidence as we wear something is equal to our change in our appearance. Right? That makes sense. And so from here, you can say that I is equal to the integral of w dt. And thus, if w is a function of time or some other variable, it's some area under its curve between two bounds is the wearability. It tells us the inclination. And so that's it for this lecture. It's a pretty short lecture, but I have some other things to discuss, including that second important announcement. So that second important announcement is that LOSC has divided into divisions. So we've made divisions of LOSC, and these are 5 main divisions: the mathematics division, the main studies division, the welfare division, the business division, and the technology division. The business division is relatively new. If you guys check the set of old courses, we don't really have any business courses, but when we start implementing business courses such as meme economy, which should be our study in here, we'll definitely put it under the business division. The mathematics division is a gigantic, or a very substantial division of LOSC, because a majority of our topics concerns mathematics. And don't worry guys, if you find yourself drafted under, or your subject you're enrolled under is drafted on, or if your name is drafted under numerous or more than one of these courses or divisions, it's alright. And professors who wish to teach in LOSC, make sure to tell me, or make sure to inform me of which division you wish to teach in. I know the LOSC is supposed to teach as one, but we need to at least have some sort of organization. So we have split LOSC in 5 divisions, and that's the second announcement. And so the next announcement is that the course syllabus for position theory is now ready. I know it's not meant for this subject, but I will link it in the description below. And I will begin the lecture sometime, maybe later today, maybe tomorrow. I'm not sure yet about my schedule. Well, I'm pretty sure it's later. Next one is our application of Euler's method. So in Reg Calculus, our next lesson will be an application of Euler's method. Sorry for the people talking in the background. So we're gonna apply Euler's method to approximate characteristics. The revised course outline is down in the description below. It's basically the same thing, but I just changed some elements of it. And so that is it for this video, and I'll see you guys in the next lecture.